Let's start with our favorite example of ammonia process. Let's say we have N2 in stream 1 going in at 1,000 gram moles per hour. Let's say we have a second flow of H2, and that H2 in stream 2, or in stream 1, inputs, equals 3,000 gram moles per hour. Of course, nitrogen plus 3 hydrogen goes to ammonia, so we've got a nice stoichiometric feed ratio. We'll keep the stoichiometry simple. Let's say what comes out, we'll have a flow rate of nitrogen. I'm going to call this stream 3, a flow rate of hydrogen in stream 3, and a flow rate of ammonia in stream 3. Let's see, if we say the extent of reaction here is psi dot, then we can do material balances. The material balances, what comes out is going to be what goes in plus generation minus consumption. So with nitrogen coming out, it's going to be nitrogen flowing in plus, well, let's see, it's going to be consumed. So this will be minus extent of reaction psi dot. So I have 1 mole for every extent of reaction. I can write that also for an H2 stream 3. We've done all this before, right? And it's H2 in stream stream 1, stream 2, minus 3 psi dot, and the amount of ammonia, NH3 in the output, is going to be 2 times psi dot. If I give you the feed in, we can turn these into numbers. So the flow rate in for stream 1 is 1,000 minus psi dot. For the hydrogen, we have 3,000 minus 3 psi dot. For ammonia, then we have 2 psi dot. Okay, so those are our material balances. Given stuff goes in, what comes out, and then let's say, what if the reaction goes to equilibrium? So let's say nitrogen and hydrogen are in equilibrium with ammonia. How do we solve this? So we know how to write an equilibrium constant. So, well, if it goes to equilibrium, I guess the question we'd want to know is, what is psi dot if it goes to equilibrium? So that's what we're going to focus on today. If it goes to equilibrium, how do we come back and get the psi dot out? All right, so what is equilibrium? So equilibrium is what? If I take a batch system and let it go to equilibrium, if I put stuff in a box and let it go until it gets completely equilibrium, things would change, and at some point it would get to steady state, concentrations would change. Say if I put ammonia and hydrogen in a box, but it doesn't, but things are, the reaction's still happening, right? We always still have some forward reactions, some back reactions, so we'll, the net flux of the reaction forward and backward are balanced, and then the net concentration change in a batch system is 0. In a continuous system, it's going to be a little bit different because the concentrations will be changing as we go through here. So, okay, so how do we do equilibrium? So, we have a chemical equilibrium constant. Everybody's seen this before, right? So, Ka is going to be the product over all species I of the activity of species I at equilibrium. raised to the power of mu I. We've all seen that expressed in terms of activities. Activities look familiar? How many people have heard the term activity before? Okay, all right, so already the notation's a little bit different. So in chemical engineering, what have you used before then? In an equilibrium constant equation?
Concentration.
Concentrations? Okay, great. So in chemical engineering, we're going to generalize a little bit. We're going to think about, so what's going to happen? You've got N2 plus 3H2 goes to 2NH3. There's some activity of these guys, some chemical activity that's going to be pushing this to the other side, and there's some activity over here that's going to be pushing it to the other side, and then when those things are balanced, they'll be in equilibrium. So what we're looking for is something about the energetics of these states and how high energy they are and how much they're going to be likely to move into a lower energy state. So that's what we're going to use activity for. So activity of species I at equilibrium for a liquid is going to be xi, or the mole fraction in a liquid. Xi liquids. So you've seen that before. In gases, it's going to be yi times the pressure, and for solids, it's going to be simply 1. So there's some assumptions here. So for gases, it'll be yi if we assume that we have ideal gases. And for liquids, we're going to assume these are ideal solutions. Okay. So an ideal gas, the approximate activity is the pressure of the gas. So this is the total pressure, and this is the mole fraction in the gas. So if you have 21% oxygen, then you have 21% of 1 atmosphere would be the activity of oxygen in the atmosphere. Some gases are not ideal. They have some interactions, and there's some different models to plug these in. So in general, we're going to use this activity because we're plugging different models. For this class, we'll assume we have ideal liquids, we'll assume we have ideal gases, and we'll assume that the solids have the activity. All right. Okay, so for ammonia, what's our Ka then? What phase does this equilibrium happen in? What phase do we have this reaction? Liquid, solids, or gas? These are gases, so I'm going to want YIP. And I would have the activities, each activity raised to the power of its stoichiometric coefficient. So I have activity of nitrogen raised to the power of the stoichiometric coefficient of nitrogen, activity of hydrogen to the stoichiometric coefficient of hydrogen, activity of ammonia raised to the stoichiometric coefficient of ammonia. So stoichiometric coefficient of nitrogen is -1, because it's in the reactants. Hydrogen is -3, and ammonia is 2. So this is going to be the activity of ammonia squared over the activity of nitrogen, activity of hydrogen cubed. All right, then the activities of each of these will be the mole fraction in the gas of ammonia times the pressure. And for nitrogen, the mole fraction of nitrogen times the pressure. And for hydrogen, the mole fraction of hydrogen times the pressure. And that will be cube, so we square. All right. So that looks like, we simplify that, ammonia squared over fraction of nitrogen, fraction of hydrogen. I've got 2 pressures in the top and 4 in the bottom, so our pressure squared on the bottom. So what do we want to run this reaction at high or low pressure? Okay, so what do we want to happen? We want to have the product to be high. We want YA to be large. We want as big a mole fraction as possible of Y. So we want this one to be big. And so Ka will be, a given temperature will be a constant. So Ka is a constant. Then, so we can rearrange this and say YA squared equals KA YN HP squared. So which way do we want pressure? Higher pressure. Okay. Another way you can see that is how many molecules in the reactants? How many molecules in the two? So pressure should push it which direction? To the right. If you were to squish those molecules together. If you've got concentrations at equilibrium, you can calculate an equilibrium constant from the concentrations. If you're given conditions, you can set the equilibrium, or given an equilibrium constant or conditions that determine the equilibrium concentration, you can set that and you can determine the concentration. Let's see, so if we knew, let's say the chemist ran this experiment and told you these are the flow rates, then you can calculate Ka for me. You can plug in over here. So we could, from these flow rates, you could tell me the compositions, the Ys, the mole fractions coming out in the stream. And then you could put the three Ys together, put the pressure, and you could calculate what Ka is. Right, so from an experiment, we could measure Ka using this expression and measurements of the mole fractions. And then we could see what Ka is. Okay, so experimentally, if we measure that, we can do that. We can also calculate Ka from scratch. Okay, so we could do this expression, we can measure the equilibrium constant. If we don't have the chemistry, we want to come up with an estimate, you can calculate Ka. So, Ka is related to Gibbs free energy of reaction. Ka is a product over all I of the activity, species I at equilibrium, is raised to the power of nu I, so that's this fraction. That equilibrium constant is also the exponential of the opposite of delta G of the reaction over KT. Let's see, this hat means molar. That's a specific quantity. Okay, so what does this mean? So this should be RT. It's K if it's a molecule, so we do that a lot with proteins. If we have a single protein molecule, we use KT, but R is the same as K, but with an Avogadro's number in there. So RT has units of joules per Kelvin gram moles is the units of R. Temperature would be units of Kelvin. So RT has the units of joules per gram mole. So RT is a energy per mole. It's a measure of about how much thermal energy is in a system because your system's at a particular temperature. So how much energy is in the gas because they're moving around in the air here because they're moving around at 68 degrees Fahrenheit. Let's see. So what are the units of delta G? They should also be in units of energy per mole. So delta G of reaction hat has units of joules per gram mole, or some kind of energy over some kind of mole. Okay, so delta G R hat is the amount conduct a mole reaction, constant temperature and pressure. So how much work does it take to get the reaction to go? So I just erased, it's here too. Nitrogen plus hydrogen goes to ammonia. How much work does it take to do that? That could be a positive or a negative number. It could be positive if we have to put energy in. It could be negative if it lets energy out. What else? Delta G of reaction hat is delta H of reaction hat minus T delta S of reaction hat. Assume you've seen G equals H minus TS. I assume you've seen that before a little bit. Okay, so you'll cover lots of this in thermal class. For here, H is, what's H? Everybody. This is enthalpy. And S is everybody. Entropy. What do those mean? Let's see. Both enthalpy and entropy can produce work. So enthalpy, what's enthalpy? That's energy. That's raw energy that, say, can be used to heat or cool something. Energy in the reaction. So that can produce work. And what's entropy? Disorder kind of. So entropy is really the count of how many states you can have. If you can only have a few states, that's low entropy. It can be many, many different states. That's high entropy. Say that molecules in the solid are all right in position. They're not moving very much. Molecules in the gas are moving a lot. Lots of. If you're moving to a situation where there's lots more configurations, that can drive work also. If you're trying to reduce the complexity or order something, that can take free energy or work to make that happen. Okay, so if delta G hat R is less than 0, then the reaction can produce work. So if I'm burning gasoline, I can produce work and I can move the car. Delta G of reaction is greater than 0, then the reaction requires work to proceed. So I have to put in energy to make this reaction happen. If delta G reaction is very, very small, much less than 0, then this reaction can proceed nearly to completion. So if the energy is if you give so much energy out, then the reaction is pretty much going to go to completion. If the free energy change is near 0, then you'll have about equal amounts on both sides. So the glucose-fructose isomerization, those two molecules have about the same energy. If they go to equilibrium, it'll be about 50-50. So if I can calculate delta G of reaction, then I can divide that by the thermal energy RT, take the exponential, and get the equilibrium constant. If I know the equilibrium constant, I can come back to this equation, Ka. If I know Ka, and over here are all my mole fractions are all going to be expressed in terms of xi dot. I can just solve for xi dot. So if I know Ka, I can solve for xi dot. I can get all the flows, right? Okay, so I can get xi dot if I just know the free energy of reaction. So maybe I need to know something about the enthalpy and entropy or the free energy of reaction. So how do we do that? Calculate the free energy of reaction. So actually this is something in my field I think about a whole bunch. I'd love to know in my protein folding, I can think about as a reaction. An unfolded protein goes to a folded protein, or a protein and a small molecule bind together. What's the energy of that? There are people that try to calculate the free energy by looking at an ensemble of all the different configurations and trying to average out the enthalpies and the entropies and calculate those all together. That's the long run technique. So we can do it for molecular simulation if you have enough computer power and the system's simple enough that we can describe it accurately. The other thing we can do is I told you we can measure these equilibrium constants, and then we can tabulate these and break them apart. So that's what people have done here. This is in your book. This is table B3. And we have standard gives energy of formation, enthalpy of formation, enthalpy of combustion. Acetaldehyde, the delta G of formation for acetaldehyde is minus 133.1 kilojoules per gram mole. So we can just look this up. So I can look that up for each species. And then we just have to add them together in our reaction to find the equilibrium constant. So delta G reaction is going to be the sum of the delta G's of formation times the stoichiometric coefficients in each column. See, the circle indicates standard conditions at a particular temperature and pressure, usually 298 and 1 atmosphere, 298 K, 1 atmospheres. You look at the table, and this table should say this is all for 298 K. So if we do the reaction, if we do the smoke reaction at 298 K, we can look up delta G's of formation, and then all we have to do is add these together and multiply by the stoichiometric coefficient. So if I wanted to say ethanol combustion, how much work is done by burning 1 kilogram of ethanol at standard temperature and pressure? Ethanol reacts with 5/2 oxygen, goes to 2 carbon dioxide, 3 water. I would want to sum each species, ethanol, oxygen, carbon dioxide, and water. So here we go. I'm going to take delta G, the standard G of formation of ethanol, oxygen, carbon dioxide, and water. And each one of those I'm going to multiply by these stoichiometric coefficients, -1, -5/2, 2, and 3. I know this is fast on the board. I can post these slides. I just didn't want to. We're just adding these things together and multiplying. And I think you've seen this before. Yes. Then I can look up these numbers in the chart. So back on this slide, I could look up ethanol and water, and I could plug in this delta G of formation. And I plug in so many kilojoules per gram mole, etc. And then I can add those up. I get kilojoules per gram mole. If I want it per kilogram, then I need to change that into kilograms at the end. You've done that before. If you have 1 mole of ethanol, I can change it to the number of grams of ethanol, and I can convert it there. So I get 28,000 kilojoules per kilogram of work that can be done by burning ethanol. So if you put ethanol into our car and use that to move the car, that's how much work I can do, and then we can calculate how fast we can accelerate and how big a hill we can go up, etc. When I ask for work, that means free energy, that means delta G. It turns out enthalpy you can do the same way. How much energy do you get from burning ethanol? So this isn't free energy, this is just plain old energy. And for that, we can look in that chart. If you remember in that chart, we also have enthalpies of formation. And you can do the change, the enthalpy of reaction per mole at standard state. It's just the sum of the enthalpies of formation, each species I, at standard state per mole. So I. So we can use the same table, pull out the H's, and we can also get, so now I'm plugging in H's, plugging in some different numbers, do the same thing, now I get 26,000 kilojoules per kilogram. So now I can calculate this delta H. From that, you can calculate S for me, so we can back out the entropy. All right, so you might be like, well, why are we doing this H? We need G. We need G to get K. Just erase that Ka equals EXP opposite delta G of reaction per mole over K over RT. there's a missing part. So here I need the free energy of reaction. Here I've calculated the free energy. You see the difference? What's the difference between what we calculated here and what we got here? Temperature. It's a tiny little zero. That little zero is really important. This is a standard state. Here we're calculating this from the table at 298 degrees, but your reaction might happen at 400 degrees. So how do we change the temperature? We need to go from knowing it at one temperature to knowing it at a different temperature. All right, let's see, Ka at non-standard conditions. So if you have a different pressure, how does pressure change your Ka? Well, we have the activities over here in this expression. There's pressure right there. The pressure comes right out in the expression here. So P is in the Ka expression for gases. Okay. For solids, it doesn't really matter because solids aren't really pressure. For liquids, it doesn't really matter, except it matters a little bit. When we're talking about an ideal solution, where the activity is just X, there's no pressure there. If I'm talking about proteins, you can pressurize a protein and you can unfold proteins by pressure. And they do this some to look at the hydrophobic forces and how that involves and how that interacts with the folding and to try and get at the water interactions. But that's a more advanced model. So for ideal solutions, pressure is not going to matter for liquids. So pressure is just going to matter for gases in this class, first approximation, but that won't always be true. We'll talk about that in normal class. For temperature, how does temperature affect this? Well, here's temperature right here. At the very least, temperature is going to scale the entropy. Okay, so if the enthalpy of reaction doesn't change much with reaction, if the entropy doesn't change much with reaction, which is it's a decent approximation, then at least the temperature is going to scale how important the entropy is relative to the energy. Okay, so at low temperatures, the energy or the enthalpy term will be important. At high temperatures, the entropy will be more important. Okay. Okay, so T affects affects delta G of reaction by scaling the entropy contribution. So this is going to bring us, so if I plot delta G or natural log of Ka, so delta G is delta G is exponential, sorry, Ka is exponential of opposite delta G over RT, so if I take the natural log of Ka and multiply by RT to get units of energy, if I plot the delta G or the equilibrium constant versus versus 1 over T, what we see is a line that looks like this. You see a nice straight line. So you can, again, in an experiment, we can measure Kas, we can vary temperature, and we can do this. So this was done late 1800s. This was done by someone named Van Hoff. And Van Hoff got the Nobel Prize for this in 1901. We still use this today. Let's see, I'm trying to get to natural log K1 over K2 over K1 equals delta H of reaction over R. 1 over T2 is 1 over T1. We're going to get, basically taking the ratio of these two, and we're going to get this equation, which is called our Van't-Hoff equation. We can also write this as natural log Ka at temperature T minus 1 over R reaction minus delta H of reaction over 298. That's it. If I do this at 298, I can solve for delta S. So from here, delta S of reaction is RT natural log KK of 298 minus divided by 298 minus delta H of reaction over 298. This is delta G. Delta G of reaction standard state minus delta reaction over 298. That's this part here. Plus delta H of reaction over T. Then I can plug this delta S back into here and these delta these RTs under there. This is the entropy term. There's the enthalpy term. We divide by T, and we can do this Ka at a standard temperature T. This is 1 over R. This is my second way of expressing that off. Okay, this first one, what I'm doing is things are in terms of 298 degrees, and in terms of the standard delta G reaction and the standard enthalpy of reaction and the standard enthalpy of reaction. The second one, I'm instead of going to 298, we're just using two different temperatures, and we're looking at how they compare to each other and using the. Turns out this slope is delta H R over R minus delta H R over R. So that's the slope. There's a minus there. So if I know two temperatures, T1 and T2, 1 over T1 and 1 over T2, I can relate these two equilibrium constants together. This is natural log Ka. Or if I know these standard state values, I can calculate it at a different temperature. Okay, where were we? So we looked at, we could calculate the standard free energy of reaction, we can calculate the standard enthalpy of reaction. With those, you can plug into the Van Hoff formula, and you can calculate at any temperature T what the equilibrium constant is. And similarly, if you know it at one temperature, you can change it to another temperature. So where were we? So we started with the ammonia example, and we could express what's coming out of the reactor as the extent of reactions. We have this formula here. This whole thing is a function, some function of psi dot, and then what we want to know is Ka, and this Ka, well, if we know what comes out, we can calculate Ka. So if we calculated Ka from the thermodynamics, we can plug in and we can find what that equilibrium constant should be. If we know a number here. So now if I know the temperature and the pressure that I run the reactor at in the ammonia process, then I should be able to go back and solve for psi dot. So what I should be able to ask you is a question like this. I should be able to say, consider an ammonia reactor fed 1,000 grams per hour of nitrogen, 3,000 grams per hour of hydrogen. If the reactor is run at 10 atmospheres, plot the equilibrium quotient as a function of the extent of reaction. So equilibrium quotient or equilibrium constant, same thing. So what I'd be asking for there is this quantity here, the equilibrium constant, the mole fractions divided by pressure. You can plug in pressure as 10 atmospheres. And we should be able to plot that as a function of how much reaction is happening. Then we could say if the reactor is run at 10 atmospheres in 750 K and achieves equilibrium, what is the extent of reaction? And we should be able to take the 750K. Well, let's see, we should be able to calculate a Ka at 298 degrees from the delta G's of reaction. And then we should be able to calculate a Ka at 750K as a function of the delta G of reaction and the delta H of reaction using Van Hoff. And then we should be able to plug that in and connect it back to our equation for the extent of reaction.